Welcome everyone. Through this video, I am going to discuss the properties of definite integral and its application. We have already taken 4 or 5 classes of definite integral. So this is my 5th class. So I am discussing board's problem as well as competitive problems also. So today I will discuss properties of definite integral and its application. This is part 2 of properties of definite integration. So first we consider some basic problems of basic but board's problem. So look, 1 0 to pi by 2 sin square x dx by sin x plus cos x 1 by root 2 log root 2 plus 1. 0 to pi by 2 cos square x dx by sin x plus cos x equals to this. And see x dx by pi by 2 root 2 log root 2 plus 1. And number d 0 to a dx by this. So all are alike. All are alike. These are most important problem for board as well as JEE main also. So we consider problem number D. So look, a dx by x plus root under a square minus x square whole square 0 to a. Now a square minus x square is within root over. So our main aim will be to omit root over using trigonometric transformation. So what is trigonometric transformation? X equals to a sin theta or a cos theta. So dx equals to a cos theta d theta. Then change of limit, x 0 sin theta 0, so theta 0 x a, this is pi by 2. So the integral equal to 0 to pi by 2 a cos theta d theta. So problem is like that, total whole square. Total whole square. So a dx equals to a cos theta d theta and one a at the beginning. So a sin theta plus a cos theta whole square. So a square is cancelling out. So cos theta d theta by sin theta plus cos theta whole square. So call it 1. Now we use properties of definite integral. So property, you know, 0 to a, we have already discussed it in previous video. Look, 0 to a equals to 0 to a f of a minus dx. So if we use this property, so cos theta, so theta is replaced by pi by 2 minus theta, and similarly for the denominator, sin pi by 2 minus theta cos pi by 2 minus theta total whole square. So after simplification we get sin theta by cos theta plus sin theta whole square d theta, this is 2. Now look, denominator is same. So if you add 1 and 2, numerator will be cos theta plus sin theta. So 1 cos theta plus sin theta will be cancelled out. So next step, 2i equals to 1 plus 2 implies 0 to pi by 2 d theta by sin theta plus cos theta. So 1 sin theta plus cos theta is cancelling out. Now you can integrate it by replacing sin theta in terms of tan theta by 2, cos theta in terms of tan theta by 2. But for this particular problem, it will be simple if we express it in terms of sin and cos. So look, 1 and 1. So divide by 1 by root 2. This is 1 by root 2 cos theta. And it is balanced by root. So 1 by root 2 outside. So d theta by This is cos theta cos pi by 4, sin theta sin pi by 4. So omitting one step, theta minus pi by 4. So if it is at the numerator 0 to pi by 2, sec theta minus pi by 4 d theta. So this is standard one. So if we if we integrate log sec theta minus pi by 4, integration of sec theta, log sec theta plus tan theta. So 0 to pi by 4. Now put the values 1 by root 2 log sec pi by 4 plus tan pi by 4 minus pi by 2, this is pi by 2 minus pi by 4, pi by 2 minus pi by 4 minus log sec pi by 4. If we put 0, sec of minus theta, sec theta, tan of minus theta minus tan theta. So 1 by root 2 log, this is root 2 plus 1 and this is by root 2 minus 1. So if we rationalize it, log root 2 plus 1 whole square. Log root 2 plus 1 whole square. So we are calculating 2i. 2i equals to these two at the beginning. So 2 into 1 by root 2 log root 2 plus 1. So what is I? I equals to 1 by root 2 log root 2 plus 1. So look, all are same problem. If we consider this I, then in second step it is cos square x. So cos square x sin square x 1. This one also. This is x. Due to presence of x, you cannot integrate it. So replace x by pi by 2 minus x and add. So they are of same type. Now look, consider problem number 2. 0 to pi by 4 log 1 plus tan x dx, pi by 8 log 2. 0 to pi by 2 log 1 plus x dx, 1 plus x square, pi by 8 log 2. So here you have to replace x by pi by 4 minus x, and second one, if you put x equals to tan theta, then two problems will be identical. So this is simple problem. You can consult any standard book. Now problem number 3, x dx by a square cos square x plus b square sin square x. X sin x dx by sin to the power 4x plus cos to the power 4x. X sin to the power 2nx cos to the power 2nx sin to the power 2nx. X dx by 1 minus cos alpha sin x. So we are using in all cases 0 to a fx dx equals to 0 to a f of a minus x dx. We have already discussed it in a previous video, so leave it. This is general result, and using it by putting particular values of a square and b square, you can form many problems. I have already discussed it in shortcut trick third. So we consider B, C or D. Suppose problem number B. So our main aim is to, in each cases, is to cancel x. So call it I. So exactly same procedure, x sin x cos x dx by sin to the power 4x plus cos to the power 4x. So this is I. Now replacing x by pi by 2 minus x, sin pi by 2 minus x, cos pi by 2 minus x by sin to the power 4 pi by 2 minus x, cos to the power 4 pi by 2 minus x. Now if we simplify, so pi by 2 minus x unchanged, and this will be cos x, and this is sin x, and this is cos to the power 4x plus sin to the power 4x dx. So call it 2. Now look, denominator is same. So we add 1 and 2. 1 plus 2 implies 2i equals to 0 to pi by 2. Look, here x sin x cos x. Here also minus x sin x cos x. So this one is cancel out, omitting one step. So cos to the power 4x plus sin to the power 4x. Now it is well-known problem of indefinite integral. So you have to multiply numerator or denominator by sec square x, or you can put sin square x equals to z, because derivative of sin square x is 2 sin x cos x. But it will be simple if we multiply it by sec to the power 4x. So this is tan to the power 4x plus 1. This is tan to the power 4x 1. So pi by 2 outside. And this is tan x sin x cos x into cos square x, tan x into sec square x dx. Now if we put tan square x equals to z, then derivative of tan square x is 2 tan x sec square x. So put the transformation, tan square x equals to z, because we directly get 2 tan x sec square x dx equals to dz by 2, and change of limit x and z, if it is 0 then it is 0, if it is pi by 2 infinity. So 2I equals to pi by 2, 0 to infinity. Now this is dz by 2 and this is z square plus 1. So pi square by pi by 4, 2 and 2, this is tan inverse z, 0 to infinity, 0 to infinity. So pi by 4, so tan inverse infinity minus tan inverse 0. So pi by 4 into pi by 2. So pi square by 8, 2i, but we are interested about I. So what is I? Pi square by 16. So 3 A, B, C, D. They are of same type. You have to cancel x. Then use rule of integration. Now we consider problem number 4. So 0 to 1 cot inverse 1 minus x plus x square dx, pi by 2 minus log 2. 0 to 1 tan inverse 1 minus x plus x square dx, log 2. 0 to 1 x cot inverse 1 minus x plus x square dx. So all are same type. So we consider problem number C. This is most general among them. So look, here only x is extra. So we consider this as I. 0 to 1 x cot inverse 1 minus x plus x square. Generally we will think it is a problem of integration by parts. But if we use integration by parts, then it will be difficult. So our main aim will be to cancel x first. So look, call it 1. So 0 to 1, 1 minus x, cot inverse, 1 minus x, 1 minus x whole square dx. So 0 to 1, 1 minus x, cot inverse. Now this 1 cancel, here it is 1, minus 2x plus x, so this is minus x plus x square dx. So call it 2. We are getting same argument, 1 minus x plus x square. So this is our advantage. So what is 2i? 2i is 0 to 1, x cancel. So cot inverse 1 minus x plus x square. So it is 2i. 2i equals to this. Cot inverse this. So this and this same, only they differ by a constant. Now look, if we integrate it by parts, then derivative of this is 2x minus 1 and 1 by 1 plus x square. So this is difficult. So our main aim will be this argument, to simplify this argument. So look, this is tan inverse 1 by 1 minus x plus x square dx. So 0 to 1 tan inverse. So 1 minus x common, x into 1 minus x, and we can write it this step to be noted. Look, denominator x common 1 minus x. This is x plus 1 minus x. X cancel. So meaning remaining same. So it can be written as difference of 2 tan. So tan inverse x plus 0 to 1 tan inverse 1 minus x dx. Now replacing this x by 1 minus x again, what we are getting? Tan inverse x dx unchanged plus 0 to 1 tan inverse 1 unchanged, 1 minus x dx. Now finally what we are getting, look, 2i equals to 0 to 1 tan inverse x dx plus second one is also tan inverse x dx. So 0 to 1 tan inverse x dx. So this is I. So integrating by parts, we get value. So this is your home task. So you complete it. So look, what inverse? This argument is, look, 1 minus x plus x square. Using formula of inverse circular function, we can, look, transform this argument in terms of x. So if it is tan inverse x only, so it is very easy to simplify by parts. So similarly, A and B. Now 5 and 6, they are same. So look, problem number B. So 0 to 1 x dx by x plus root under 1 minus x square into root over 1 minus x square. So due to presence of root over 1 minus x square, we put a trigonometric transformation. So what is trigonometric transformation? X equals to sin theta. So dx equals to cos theta d theta. So what is I? X is sin theta, dx is cos theta d theta, and this is sin theta, this is again cos theta, and 1 minus sin square theta cos theta. And what is the change of limit? If it is 0, 0, if it is 1, then pi by 2. So 0 to pi by 2. So cos theta cancel, sin theta d theta by sin theta plus cos theta d theta. Now it is simplest problem. Replacing theta by pi by 2 minus theta, you get cos theta and denominator unchanged. So proceeding in this way, we get answer. What is the answer? Upper limit minus lower limit by 2. So this is I. Then transfer in terms of pi by 2 minus theta. So this will be cos theta d theta, and this is sin theta plus cos theta. So omitting one step, what will be 2i? 2i equals to 0 to pi by 2 d theta, that is pi by 2. So I equals to pi by 2. So this one is simple. So second one, first one is exactly same. Here transformation is x equals to tan theta, because tan theta transform infinite limit in terms of finite limit. So 6a and b, this is also using property upper limit minus x, lower limit, upper limit minus x. We have already discussed this problem, this one also, using 0 to pi by 2 log sin x dx. So look, this problem, here you have to use a suitable result, 6b. So I equals to, consider it, 0 to pi by 2, 2 log sin x minus log sin x sin 2x dx. So if we simplify it, 0 to pi by 2 log sin square x minus log 2 sin x cos x dx. So this is 0 to pi by 2. Now log a by b, log sin square x by 2 sin x cos x. So 0 to pi by 2 log sin x by 2 cos x. So now you know a useful result. So we have already proved it, log sin x dx equals to pi by 2 log half, pi by 2 log half. Now we can write it in this form, 0 to pi by 2 log sin x minus 0 to pi by 2 log 2 dx, using property of log, 0 to pi by 2 log cos x dx. Now this and this same value, pi by 2 log half. So this cancel and use. So if we interchange x by pi by 2 minus x, this cancel. So log 2 outside and you get value of the integral. So now we consider two alike problems. 1 by e to tan x t dt by 1 plus d square, 1 by e cot x dt by 1 plus d square, and then fx equals to 1 by x log t by 1 plus d dt. Prove that fx plus f1 by x equals to log x whole square by So they are exactly same. So suppose consider problem number 2. So fx equals to 1 to x log t by 1 plus t dt. So what is f of 1 by x? So 1 to 1 by x log t by 1 plus t dt. So only x is replaced by 1 by x. Now we replace, we put a transformation. So suppose t equals to 1 by z. So if we put this transformation, look, this limit 1 by x will be x. So what is dt? Minus 1 by z square dz. So 1, if t equals to 1, then z equals to 1. T equals to 1 by x, z equals to x. Log 1 by z, 1 plus 1 by z. And this is minus 1 by z square dz. Now this is 1 to x. This is log 1 minus log z. So log z, log 1 is 0 and 1 plus z into z dz. Omitting one step. So look, log 1 minus log z. Log 1 is 0, though this minus is plus. So this z will be at the numerator. 1 z is cancelled out. 1 to x. Now we can change the limit. This is dummy variable z. 1 to t log x by x into 1 plus log x. Sorry, log t by 1 plus t into t dt. So you may think there is a transformation t equals to 1 by z. So how this one is 1 by z? But look, we are using property of properties of definite integral. So first we may interchange this dummy variable z in terms of y. Then y to t we get this one, omitting one step. Now this is f1 by x. Now if you add, this is 2 fx plus f1 by x. So if we add these two, so fx plus f1 by x, look, limit is same, 1 to x, both limit, and first one is log t by 1 plus t, and second one is log t by t into 1 plus t, and total dt. So look, so 1 to x log t by 1 plus t common, 1 plus 1 by t dt. So finally, so log t by t dt. So look, simple result, log t by t. Because if we put log t equals to p, so 1 by t dt equals to dp. So 1, log 1 is 0, and this is p is log x. So log t is p, so p dp. So this is p square by 2, 0 to log x. So log x whole square by 2. Log x whole square by 2. So for the problem number 1, look, so this one unchanged. We do not change this one. So for the second integral, we put a transformation t equals to 1 by z. T equals to 1 by z. So you complete this one. Now we consider definite integration considering functional relation. Look, if fx be a function satisfying fx plus x square fx equals to 0, then prove that sin theta to cosec theta f theta d theta 0. B, a fx plus b f1 by x, 1 by x minus 5, a not equals to b, then 1 to 2 fx dx. This is simple, but it will take time. So you have to find fx first, you know, replacing x by fx, x by 1 by x, you have to find fx. Then integrating, we get result. Now see, if R2R be a continuous function such that, this is such that f of x equals to f2x for all x belongs to R. If f1 equals to 3, then minus 1 to plus 1 f of fx dx equals to what? So consider problem number 1. So write I equals to sin theta to cosec theta f theta d theta. Now sin theta to cosec theta Look, what is f theta? F theta is, fx is minus 1 by x square f1 by x. So f theta is minus 1 by theta square, f of 1 by theta d theta. So what is f1 by x? Fx minus 1 by x square. So minus 1 by theta square, f 1 by theta d theta. Now this is f1 by theta. So put a transformation, reciprocal transformation, theta equals to 1 by phi. So what is d theta? D theta equals to minus 1 by phi square d phi. So change of limit, sin theta. So if it is sin theta, this is theta, phi equals to, this is cosec phi, and this is reciprocal, so this is sin phi, minus phi square, 1 by theta equals to phi, minus phi square, f of phi, and this is again minus 1 by phi square d phi. So finally what we are getting, you look, cosec phi to sin phi. So this one minus 1 as plus f phi d phi, f phi d phi. So if we simplify it, look, earlier problem in 1, this is sin theta at the lower limit, as the lower limit, this is phi. So we can consider this as minus sin phi by cosec phi, f phi d phi. Then we change the limit phi to suppose x. So sin x, and this is cosec x, fx dx. So using properties of definite integral. Then again change x to theta. So sin theta, cosec theta, f theta, d theta. So this is, look, our original integration, I equals to minus I. So 2I equals to 0, I equals to 0. So look, f theta, use functional relation and use reciprocal transformations. Now we consider another set of problem. Look, sin inverse root x dx by x square minus x plus 1 dx equals to pi square by root n, sin n. So I equals to 0 to 1 sin inverse root x by x square minus x plus 1. So to omit root over, obvious transformation is x equals to theta square. So dx equals to 2 theta d theta. So what is the change of limit? 0, 0. If x equals to 1, theta also 1. So sin inverse sin theta dx 2 theta, sorry, x equals to sin square theta. So sin inverse sin theta is theta. So dx equals to 2 sin theta cos theta d theta. So change of limit 0, 0, then 1, this is pi by 2. So sin inverse sin square theta, so this is theta, 2 sin theta cos theta d theta, and this is sin to the power 4 theta minus sin square theta plus 1. So 0 to pi by 2, theta 2 theta sin theta cos theta d theta. Now sin to the power 4 theta minus sin to the power 4 theta plus cos square theta. Now look, we have to cancel theta. So using properties, so same, so what is our property? So replace theta by pi by 2 minus theta. So 2 into pi by 2 minus theta, sin pi by 2 minus theta, cos pi by 2 minus theta d theta. And this is sin to the power 4 pi by 2 minus theta, cos square pi by 2 minus theta. So this is typical problem. This is not simple, this is typical. Now 0 to pi by 2, 2 into pi by 2 minus theta. So this is cos theta, this is sin theta. So sin to the power, this is cos to the power 4 theta plus sin square theta. So look, denominator is not same. Look, sin square theta, it is cos square. This is sin to the power 4, this is sin square theta. But you know, there is a well-known problem of trigonometry. Sin to the power 4 theta plus cos square theta is equivalent to cos to the power 4 theta plus sin square theta. So we can write it in this form, 0 to pi by 2. So sin to the power 4 theta plus cos square theta, and numerator unchanged. 2 into pi by 2 minus theta into cos theta sin theta d theta. Cos theta sin theta d theta. So call it 2. Here there is a omission of step. Look. So if we add 1 and 2, so what we are getting? 2I equals to 2 outside. So 0 to pi by 2. Pi by 2 sin theta cos theta by sin to the power 4 theta plus cos square theta. Now you complete this one. Now it is simple. Put sin square theta equals to p. Put sin square theta equals to p. And integrating we can transform it into standard form. Look, this is p square and this is 1 minus p and this is dp. So you can easily integrate it. Now this one same. This one is simple problem. F dash x equals to fx, integrate and find fx, put the value. So consider the last one. So log 2 root over log 3 x sin x square by sin x square plus sin log 6 minus x square dx. So here integration in terms of limit of integration. So transformation is x square equals to z. So what is x dx? dz by 2. Now look, this limit in terms of z, log 2 to log 3. So sin z. So look, problem will be like that. I think this is third bracket sin x square, third bracket, and this is third bracket. This is also third bracket. What is third bracket? Third bracket is greatest integer function. So sin z third bracket, and this is sin z third bracket, that is greatest integer function, sin of log 6 minus z. This is dz. Then we replace, this is 1, replacing, look, now it is very simple, replacing z by upper limit plus lower limit minus z. So upper limit plus lower limit, log 2 plus log 3. So sin of log 6 minus z, third bracket, and denominator is sin of log 6 minus z. This is third bracket, and this is sin of z, third bracket, dz. So this is 2. If we add 1 and 2, I think there is a half is at the denominator, half. So 2I equals to, so half, log 2 to log 3, and this is dz. So dz, why dz? Sin z, sin log 6 minus z, third bracket, sin z plus sin log 6 minus z, third bracket. So this is half of integration log 2 to log 3 dz. So half of log 3 by 3, half of log 3 by 2. Then calculate I. So this is also, so look, simple, but you need some trick. So today we have discussed some important problem of definite integral using its property. If you enjoyed the video, you please share and subscribe this to my channel. Thank you.